Hello, my precious friends. I really hope that you are doing great. Welcome to today's class. It is our fourth lesson on the ninth topic of Form 3 work, which is called quantity of heat. As usual, let me commence by giving the quote of the day, which states that your current situation is not your final destination. We shall discuss that quote at the end of our class today. So today we're looking at the specific latent heat and change of state. So we'll start by looking at the heating curve for water. So between point A and point B, water exists in solid form. So of course the solid form of water is what we call the ice. So from negative, if you heat water from negative 5 degrees up to 0 degrees, of course from when the temperature of water is below 0 degrees, that is we are talking of solid ice, or water exists in form of ice, and we know that ice is usually in solid form. So the heat that is absorbed is actually used to heat, that is to increase the temperature of water, that is of solid ice, from negative 5 degrees up to 0 degrees. Then between point B and C, you can see that between point B and C, we are having a constant temperature of 0. We know that the melting point for water is actually 0 degrees. So that is the solid ice will simply melt. It will change its state from solid ice, that is the solid form, up into the liquid form. So between point B and C, there is going to be heat which is absorbed, that is going to be used in the process of converting the solid ice into water, that is the liquid water. And the heat that is absorbed between region B and C is what we call the latent heat of fusion. Then of course, if you continue heating water between point C and point D, now the water exists in liquid form, that is the water. Then between point B and that is point D and point E, you can see that it is occurring at a temperature of 100 degrees, and we know that the boiling point of water is 100 degrees. So between point D and point E, the water exists in gaseous state, that is what we call the steam. So the same thing happens for the cooling curve, that is for the naphthalene. So remember, the quantity of heat that is absorbed during the process of heating will be equal to the quantity of heat that will be released during the process of cooling. So if you cool naphthalene from a maximum temperature, that is between point O and point P, so in this particular case, the liquid naphthalene actually cools from the maximum point possible, that is at the highest temperature possible, up to this particular temperature here, up to the melting point of naphthalene. So between point P and Q, simply naphthalene will be changed, that is during the process of cooling, the naphthalene will change from liquid state, that is the liquid naphthalene, into the solid naphthalene. So the heat that is released in this particular process will be equal to the heat that was absorbed between point B and point C. Then so between P and Q, actually we are talking of the solid naphthalene, that is the liquid naphthalene has actually melted and therefore solidified. Then between point Q and point R, this is now the solid naphthalene, which is actually cooling. So we are saying that between point C and, that is between point BC and point DE, you can see our BC and DE. So between these particular points, actually the temperature is remaining constant. For example, the temperature at point D is 100 degrees. The temperature at point E is also 100 degrees. So between this point, the temperature is remaining constant. Similarly, the temperature at point B is 0 degrees. The temperature at point C is also 0 degrees. So between point B and C and point D and E, clearly, also between point P and Q, clearly you can see that the temperature is remaining constant. So between point BC and point DE, the change of state is not accompanied by a change in temperature because the temperature remains constant. Then between point BC, that is for the heating curve of water, we know that the water actually melts at 0 degrees. So between point BC, we are talking of melting, whereby the process in which the water, that is the solid ice, will be converted into the liquid state, that is the water. So the heat that is absorbed, or the heat that is required to convert the solid form of water, which is actually ice, into liquid state of water, the heat that is absorbed, we call it the latent heat of fusion, which simply refers to the heat required to change the state of a material from solid to liquid state, of course at constant temperature, because you can clearly see between point B and C, the temperature is actually 0 or it is remaining constant. Then when we talk of specific latent heat of fusion, then we must specify the quantity of mass of water or the mass of the substance that we are talking about. So specific latent heat of fusion will just be the quantity of heat required to change a unit mass. Remember, a unit simply means one quantity of that particular mass. So because we are specifying the mass, that's why we are adding the word specific latent heat of fusion. But if we don't specify the mass, then we are simply talking of the latent heat of fusion. But when we talk of a specific quantity of mass, for example, a unit mass, that is a unit mass, then we must specify. So specific latent heat of fusion is simply the quantity of heat required to change a unit mass of a solid to liquid at a constant temperature. So from this definition, we can see that the specific latent heat of fusion, which is denoted by LF, that is the specific latent heat of fusion, will be given by the quantity of heat that is absorbed during that process divided by the mass of the solid. For example, in this case, we are talking of the solid ice. So divided by the mass of the ice or the solid that is changed into the liquid state. And because we know that the SI unit for quantity of heat or the heat is actually joules and the quantity, the SI unit for mass is actually kilogram, it means that the quantity, that is the SI unit for specific latent heat of fusion, will simply be equal to the quantity of, that is the SI unit for the quantity of heat divided by the SI unit for mass, which is joules divided by kilogram, which gives us joules per kilogram. So those are the SI units for specific latent heat of fusion. So you can also make Q subject of the formula by multiplying both sides by mass. So we can talk of Q being equal to the mass of the ice that was changed into the liquid state, or the mass of the solid that was changed into the liquid state, multiplied by specific latent heat of fusion. Then between point DE, we can see between DE, we are talking of 100 degrees. Then we know the boiling point of water is actually 100 degrees. So between point DE, what will happen is that the water will be changed from the liquid state into gaseous state, that is into steam, or what we are calling the water vapor. So actually point DE is the boiling, that is the boiling point of water. Of course, it also takes place at a constant temperature of 100 degrees Celsius. So the heat that is absorbed during process DE is called the latent heat of vaporization. So vaporization from the word evaporation. We know that evaporation is simply the change of state from liquid to gas. We are also talking of water changing from that is the liquid water into gaseous water, which is actually steam or the water vapor. So the heat that is absorbed at that point, we call it the latent heat of vaporization, which simply refers to the heat required to change a liquid to vapor at a constant temperature, or the heat required to change a liquid to actually a gaseous state at constant temperature. Like in this case, the constant temperature is actually 100 degrees Celsius. That is for the case of water. Then if we specify the mass of the liquid that is being changed into the gaseous state, then we talk of specific latent heat of vaporization. Therefore, specific latent heat of vaporization will be defined as the quantity of heat required to change a unit mass of a liquid to vapor at a constant temperature. Then, of course, from the definition, we can also see that specific latent heat of vaporization, denoted by LV, will simply be equal to the quantity of heat that was absorbed, that is to change the liquid into gaseous state, divided by the mass of the liquid that was changed from liquid state to steam or the gaseous state. Clearly, you can see that specific latent heat of fusion, its SI unit will be, that is specific latent heat of vaporization, its SI unit will simply take the SI unit for a quantity of heat Q divided by the SI unit for the mass, that is, which is in kg. Therefore, the SI unit for specific latent heat of vaporization will be given by joules per kilogram. So joules per kilogram, those are the SI unit for specific latent heat of vaporization. We can also make Q subject of the formula, so that the quantity of heat that is absorbed for a liquid to change to gaseous state will be given by mass of the liquid that was changed from liquid state to gaseous state, multiplied by specific latent heat of vaporization. Next, we look at determination of specific latent heats. So it can be determined by either use of the method of mixtures or by electrical method. So let's start by looking at specific latent heat of fusion using the method of mixtures. That is how we can determine it. So in this particular method, a piece of ice, of course, you record the initial temperature for the ice. You also record the initial temperature for the water. After that, you drop the piece of ice into water. Then, of course, you stir it. Then you also record the final temperature of the mixture. So because the ice was at a smaller initial temperature, we expect the ice to gain the heat. Then because the water was at an initial temperature which is higher than the temperature of the ice, in this case we expect the water to lose heat to the ice. Then of course the purpose of the stirrer is simply to ensure that there is uniform temperature, that is to ensure that the melted ice and the water, of course, they mix properly so that we have a uniform final temperature. Then of course the thermometer is simply for detecting any temperature changes, also for measuring the final temperature and the initial temperature of both the ice and the water. So a piece of ice is dropped into water in a calorimeter a few degrees above the room temperature, say T initial. Then the temperature falls to say T final, that is TF. So if the mass of water was M1 and the mass of water plus the piece of ice was M2, then it simply means that the mass of ice will be given by the mass of water plus the ice minus the mass of water alone. So M2 minus M1 will give us the mass of the ice. Then from the law of conservation of energy, the heat which is lost must be equal to the heat that is gained. So because the water was at an initial higher temperature, we expect the water to lose the heat. Then because we know that the temperature of ice is usually either 0 or below 0 degrees, it simply means that the ice was initially at a smaller initial temperature as compared to water. So if the initial temperature for the ice was small, it simply gives you a clue that the ice gained the heat. Then because the initial temperature for water was greater than the initial temperature for the ice, it means that the water actually lost heat. Therefore, if we are talking of a copper that is a calorimeter, which is ensuring that no heat is being lost to the environment, then if we follow the law of conservation of energy, all the heat that is lost by water must be equal to all the heat that is gained by the ice, or the heat that was used to melt that ice. So the heat lost by water must be equal to, so the ice usually gains heat in two forms. One, we'll talk of the heat gained by the melting ice. So the heat gained by melting ice, this is the heat that is used in the process of converting solid ice into water. Remember, the ice, when we talk of melting, a substance is changing from liquid, that is the solid state, to liquid state. So the heat that is absorbed at a constant temperature to change all the ice, that is to melt the ice into liquid, that is what we are calling the heat gained by the melting ice. Then once all the ice has melted to water, then we'll talk of the heat gained by the melted ice. So ice usually gains heat in two forms. So heat gained by melting ice, that is the heat that is used in the process of melting ice, will be given by mass of the ice multiplied by the specific latent heat of fusion for that particular ice. Then plus the heat gained by melted ice, because we are talking of melted ice, that is actually water, but which has been obtained from the melted ice. So we'll talk of the mass of the ice, because when a substance melts, actually its mass does not change. Then multiplied by specific latent heat multiplied by specific heat capacity for the water. Remember, ice is just water in solid form. Then multiplied by the change in temperature for the ice. So next, let's look at an example involving specific latent heat of fusion. So our example reads that in an experiment to determine the specific latent heat of fusion of ice, 0.025 kg of dry ice. So the mass of ice we are given as 0.025 kg at 0 degrees Celsius. So the initial temperature for the ice is 0 degrees Celsius. Is melted up in 0.2 kg of water. So that is, of course, the mass of water. We are given as a mass of water is 0.2 kg at 21 degrees Celsius. So that is the initial temperature for the water is 21 degrees Celsius in a copper calorimeter of mass 0.25 kg. So mass of the copper calorimeter is 0.25 kg. Then because the water was initially placed in the copper calorimeter, it simply means that the copper calorimeter will assume the initial temperature for the water. So if the initial temperature for the water was 21 degrees Celsius and the water was placed in the calorimeter, it simply means that the initial temperature for the copper calorimeter will also be equal to the initial temperature for the water, which is equals to 21 degrees Celsius. Then, if the final temperature of the mixture fall to that is 11 degrees Celsius, so that is T final for the mixture is 11 degrees Celsius, that is the final temperature. What is the specific latent heat of fusion of ice? Then you are given that the specific heat capacity of water is 4200 joules per kilogram per Kelvin, and that of copper calorimeter is 400 joules per kilogram per Kelvin. So from the law of conservation of energy, heat lost must be equal to the heat gained. So to determine the substance that is gaining and losing heat, we simply compare the initial and the final temperatures. So the final temperature is 11 degrees Celsius. So any substance which has an initial temperature which is greater than which is greater than 11 degrees Celsius, it means that substance is losing heat. So in this case, you can see the initial temperature for water was 21 degrees Celsius. So of course, 21 degrees Celsius and the final temperature of the mixture is 11. So because the final temperature is smaller than the initial temperature for the water, that tells you that water is losing heat in this case. Similarly, because the initial temperature for the copper calorimeter was 21 degrees Celsius and the final temperature of the mixture is smaller than 21 degrees Celsius, it means that both the water and the copper calorimeter were losing heat. Therefore, heat lost by water plus the heat lost by the copper calorimeter must be equal to the heat gained. We said that if a substance gains heat, its final temperature must be greater than the initial temperature. And you can clearly see that the initial temperature for the ice was 0 degrees Celsius. The final temperature of the mixture is 11 degrees Celsius. So because the initial temperature is smaller than the total final temperature, it means that the ice was actually gaining heat. So what tells you the substance that is gaining or losing heat? You simply compare the final temperature with the initial temperatures. So if the initial temperature is smaller than the final temperature, that substance must be gaining heat. Then if the initial temperature is larger than the final temperature, it means that substance must be losing heat. It must be losing heat. So the heat, it means that the heat was gained by actually the ice, which made it to actually melt. Because if ice exists at a temperature which is greater than 0 degrees, that ice will simply melt into water. Then from a previous page or slide, we have simply said that ice usually gains heat in two forms. So it gains in terms of the heat gained by the melting ice, that is the latent heat of fusion, and the heat gained by the melted ice. So the melted ice in this case represents the water that has been converted into liquid state, that is from the solid state, which was actually the ice. So heat lost by water will be given by mass of water multiplied by specific heat capacity of water times change in temperature for the water. Heat gained by the copper calorimeter will be mass of copper calorimeter times specific heat capacity of the copper calorimeter multiplied by the change in temperature for the copper calorimeter. Then of course, heat gained by melting ice will be equal to the mass of the ice multiplied by specific latent heat of fusion. Then heat gained by melted ice will be given by mass of ice multiplied by specific capacity of the water, that is the water that was converted into that was converted from the solid state of ice into water, multiplied by the change in temperature for the ice. So we are talking of the mass of ice because this is the water that has been converted to, that is from the solid state of ice into the liquid state, which is simply water. So the mass of that particular water that was converted to the liquid state from the solid state will be equal to the mass of the ice. That is why we are using the mass of the ice. But because it is still water, we'll simply use the specific capacity of water, which is simply W water. Then we substitute the values that we have. So mass of water was 0.2 kilogram times specific capacity of water. We are given as 4200. The change in temperature for the water will simply take the larger value and the smaller value. So the initial temperature was 21, the final temperature was 11. So the difference between 21 and 11, you simply take the larger temperature, which is 21, minus the smaller temperature, which is 11. Then plus the mass of copper calorimeter, we were given as 0.25 kg multiplied by specific capacity of the copper calorimeter. We are given it as 400 joules per kilogram per Kelvin. The change in temperature for the copper calorimeter is same as the change in temperature for the water. So the difference between the initial temperature and the final temperature. Then when we are subtracting, we are interested with the positive value. So I'll simply take 21 minus 11. Then mass of ice we were given as 0.025 kg. Then specific latent heat of fusion, that is what we want to find. Then plus the mass of ice, of course, is 0.025 kg times specific capacity of water was simply 4,200 joules per kilogram per Kelvin, multiplied by the change in temperature for the ice. Initially, the ice was at 0 degrees Celsius, then the final temperature of the mixture was 11. So the change in temperature for the ice will be 11 minus 0. Then, of course, 0.2 multiplied by 4,200, then 21 minus 11, you will simply get 10. Then, of course, 21 minus 11, you'll also get 10. Then, if you take 11 minus 0, you'll simply obtain 11. You will obtain 11. So that if you take 0.2 multiplied by 4,200 multiplied by 10, you'll obtain 8,400. Then if you take 0.25 times 400 times 10, you'll obtain 1,000. Now, if so that will be equal to 0.025 multiplied by specific latent heat of fusion, that is LF. Then that is plus, of course, if you take 0.025 LF, you'll simply obtain 0.025 LF, then plus 0.025 times 200 times 11, you'll obtain 1155. Then if I take 8,400 plus 1,000, you'll simply obtain 9,400, being equal to 0.025 LF plus 1155. Then if I collect the like terms, I'll simply take 1155 towards the left hand side, so that I have 9,400 minus 1155 being equal to 0.025 LF. Then if 9,400 minus 1155, I'll simply obtain 8245 being equal to 0.025 times LF. So if I make LF subject of the formula, I'll divide both sides by 0.025. So LF will be equal to 8245 divided by 0.025, which will give me 329,800 joules per kilogram per Kelvin. Therefore, the specific latent heat of fusion of ice was into standard form. So this will be 3.298 multiplied by 10 power 5 joules per kilogram per Kelvin. Then lastly, I have an exercise that I recommend you should try at your own free time to get the understanding of the concepts that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that your current situation is not your final destination. The quote is encouraging us not to let our current circumstances to define us. Remember that anything is possible provided that you are willing to work on your weaknesses until they become your strength. Therefore, in order to succeed, you need to trust the process, and more importantly, to have the patience to wait for the results you've been working hard for. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. In case you know any student or anyone that you honestly think could benefit from this content, kindly refer them to Kind Tuition Academy or share my link to them. Thank you for the continued support. I really appreciate. Until next time, this is Kind Tuition Academy.